What's kind of amazing about this alternate implementation of Prim's algorithm is that it is almost exactly the same as Dijkstra's algorithm. The only difference between the two is that Dijkstra's cares about the distance from the source, and Prim's cares about the distance from the tree that you're building. So for example, when it comes to visit order, Dijkstra's algorithm, it visits the vertices in the order of the distance from the source, and Prim's will visit in order of the distance from the tree. Same deal with relaxation. In Dijkstra's, I have an edge. I want to know, should I use it? Well, I consider, is it better in terms of the distance from the source? And if so, yes, let's adopt it and use it. In Prim's algorithm, we instead think about the distance from the tree. Okay. Now, you'll note if you look very carefully at the code, which I'll show here, they're a little different, but they are basically exactly the same. And you can actually write them so that they are exactly in parallel, but I just decided to write this one up a little differently. And you can compare them if you want, but you're not expected to know this code in and out. But this hopefully will make things a little more concrete if you are curious to know what it looks like at the very bottom. So a implementation of Prim's algorithm might look like this. We have an edge2 array, a distance2 array, a marked array, and a fringe. Now this marked array is not strictly speaking necessary, and if you look at the Dijkstra's implementation from the previous video or lecture, you'll see I didn't have a marked array, and you can see how I avoided it. But here I'm going to do it just because. We set the distance to the source to 0, all the other distances to infinity, and then we add all of the vertices to the fringe. Then as long as there are vertices left, we're going to remove the closest vertex, which will be the source at first, and then it'll be other vertices. And then we're going to scan all of the edges in the graph from that vertex v. So what does scanning mean? This is just the inner loop here again. Scanning means we are going to take a graph and a particular vertex, and then we're going to first mark that vertex as true. So this is saying, okay, you are now part of the MST club, and we're implicitly at that point committing ourselves to using the edge2 value that was already pointing at that vertex, if any. We will then figure out what the other vertex is on the end of this edge. So this is just the API from the optional algorithms textbook, not super important, but basically W is our target on the other end of the edge. If that vertex was already marked on the other end of the edge, don't do anything. Otherwise, we'll actually compare the edge weight to the distance, and then we'll set the distance to the edge2 and change the priority if the edge is actually accepted by the relaxation process. And that's all Prim's algorithm looks like roughly. So here's a question for you. What's the runtime of that algorithm? And what you could do is, actually I would encourage you to go back and look at how we did the runtime in the Dijkstra's algorithm video. And it turns out that the analysis here will be very similar. And so you should assume, by the way, I think that the cost model you want to think about is the priority queue operations. And here are some tips. All right, so hopefully you had a chance to think about it. Turns out the analysis is exactly like Dijkstra's algorithm. We will look at our priority queue operation counts, and we're going to assume we have some kind of binary heap priority queue. So we have v insertions. All the vertices get inserted exactly one time, and each of those insertions takes big O of log v time. The deletion operation, each vertex gets removed exactly once, because that's our condition for being done, and that costs big O of log v time, so it's log v in the worst case. And then in terms of decreased priority operations, that's going to be big O of E decrease operations. So if every relaxation succeeds, then the decreased priority operations will be exactly E in count, but it certainly can't be any more. And each of those will cost big O of log V. And so the overall runtime of our algorithm is just going to be V log V plus V log V plus E log V. And assuming a typical graph where the number of edges is much larger than V, then the answer is just going to be big O of E log V. And that's it. That's a runtime. So that's the more practical implementation of Prims. But the conceptual part is really the more important part. But I think this is really neat to see how using a little cleverness and using some fancy data structures like our priority queue, we can make an algorithm that is much faster than the naive implementation.